my fellow data scientist colleagues. I'm the one who know this nickname of vvmatorin, and I'll be going through the codes that got me the third place in the founder sales prediction competition. It wasn't the same code that achieved me as the seventh place on the public leaderboard, but it also did quite well there, reaching about 9th or 10th place. But it also proved to be consistent between the leaderboard shakeups, which obviously happened due to the change of the test dataset that was used for evaluating our performance. So I'll be going through this code cell by cell, and I'll start by loading the data that we were provided at the start of the competition. That data included store ID. It was basically a time series for multiple stores which were separated by different store IDs for about 2 years of data. Then card ID, which pointed which card was used for the transaction, the card company, which were around 8 different values, transaction date, transaction time, installment term, which was used to point out which of the payments or transactions were made in installments. A region, a field that contained really a lot of missing values and that indicated, well, basically the region where the store was located, the type of business that was corresponding to the store, and the amount of the transaction. I also added date fields right at the start, which basically combined transaction date and transaction time fields. So, moving on to the preprocessing step, I started by removing all of the negative values from the data because I thought that it would be quite hard to gain a model which would predict both installments and just aggregated amounts, sheer amount of transaction sum. Obviously, the negative values corresponding to the transactions which were paid in installments, so there were basically multiple transactions that corresponded to the same original transaction. I think the code here is quite simple. I was just matching the transactions with the negative amounts, with the positive amounts, and then removing the transactions from the positives that corresponded to the installments. So moving on from here, I think it's quite clear and you can basically understand all the logic from the code that was located here. I moved on to dropping the columns that I obviously didn't need anymore, which is the date, because I already combined the transaction date and transaction time, and the installment term. The drop of the installment term can actually be a bit confusing and can be discussed because I think the revenue of the store can be estimated pretty well by the amount of transaction which were obviously done in installments for the store. But I thought, and by analyzing and building some charts from the data, I actually basically figured out that it was quite hard to gain insight from that amount, and it was quite hard to divide stores in some categories based on it. So I decided to drop it. And then moving on from here, I decided to add some additional features based on the field's type of business, which was provided in the original dataset. Basically, I separated all of the businesses first of all into the business area, which was a general area where the business was held. So I separated all of the fast foods, restaurants, or just food shops under the category foods, all of the health, or I don't know, masseurs, parlor, etc. under the health and beauty category, and etc. all the cinemas and attractions under the entertainment category, etc. And also I added a field kind of service, which was basically to find the difference between the manufacturers of the goods, the ones that were provided utilities to retail customers, that were provided some kinds of service. And I think there are only 4 types of these categories. So I did this manually and then I organized all of them into a CSV which I'm downloaded here, and then I basically just merged it with my original data based off the type of business field. Moving on, I also encoded all of the string variables as categories, and so here is the first point, that I didn't change the missing values at all. I just encoded them as a separate missing category, and that obviously impacted the performance of my model in some way. But imputing the missing values is always a huge risk, especially when there is a high amount of missing values. So I thought that imputing them as a separate category, even if it was quite meaningless for the overall split and gain, at least preserved the original state of the data that we were provided. So then I basically added some date-related features. I used the library work calendar that contains a lot of useful information about holidays, work days, or weekends, and obviously the national holidays for different countries, which was the most important thing in this research, because we were focusing only on Korean stores. And so I added the information about the holidays and the weekdays and the work days for each of the transactions to basically understand whether the transaction was done during the weekday or the holiday. I could have also added features like year, date, and obviously things like that. But such features are pretty hard to aggregate when we are moving to the aggregation part and aggregating all of the data by 3 months periods, which I will obviously explain a bit later. So here we got for each of the transaction, we know whether the date for this transaction is a holiday or not, whether it's a work day, and which of the weekdays it is, obviously from Monday to Sunday. And also I set date and index to perform some of the calculations in the next parts of preprocessing. After that, I added some of the features that were for each of the stores, which were some kind of aggregation of data that we got about the transaction amounts of the store over the full time series period. Here, I think lies one of the potential issues, even though it didn't affect the outcome of the model. I think it could impact it negatively, which is the thing that here we introduce one of the leaks, because obviously the field sum includes all of the sum for all of the transactions that we're having. So further in this code, when we're doing the validation part and splitting the data into training, test, validation datasets, and training our model based on the outcome. These sum fields obviously introduce leak because it includes the data from the next, if we're taking data for the first couple of months, it obviously will include the data from the next ones as well. So it introduces a leak. Obviously, by removing it, we may have actually decreased the performance of the model. But in the later versions of this code, I actually removed it or replaced it by its ranking based on it, even though it didn't perform as well. So then we went ahead and called some of the categories, basically splitting all of the categories that were encoded in one column into the multiple columns. I did it for the card companies and for the weekdays, gaining, basically 8 and 7 different columns for both of them. And moving on from the step, we get to the step which was the main part of this code, and which is the data analysis part and feature processing. So, to use the model, I use a light gradient boosting model for this computation because it's beginning now to try to do with Facebook Profit and with Pyramid Arima, which is a Python implementation for the After Arima library from R. But they actually proved to be quite inefficient for some of the stores because many of the stores had quite inconsistent sales results between data or had some periods where the data for sales is either missing or the store is having no sales at all. So the trends and the rest all things proved to be quite inefficient for the pure time series prediction. So I decided to go with the approach of using a gradient boosting. And the first step is the splitting of all of the data in the equal parts for 3 months. I use the frequency of quarters for the quarter year that starts at December. So obviously that would be winter is the first quarter, then spring is the second, and so on. Here I introduced basically the constant based on which I will be doing the split. I got all the stores, all of the unique stores, and all of the unique groups that were based on the quarter. Moving on from here, I went through each store, and for each 3 months period of the store, I took the information that for all of the transactions for the store during that period, and I added some features based on those transactions. So what those features included is, first of all, decay rates. The decay rate is basically an indicator of how the transaction amounts changed over the period since the start of the period to the end of the period. So what we are doing here is we're sampling all of the data based for different days amounts from 1 day, 7 days, 14 days, and so on. We're aggregating the transaction amount for that data, and then we're adding an additional column which is basically a difference between each period and the previous period. After that, this one is for the date differences. This one is for the differences in the amount between periods. And after that, we'll calculate the decay. We take all of the differences that we find across all periods, obviously for the same granularity of 1 day or 7 days, and so on. And we've just calculate an average for the difference. The decay can be calculated in multiple different ways. It can be just left as an average difference. Then it can also take into account time. So here I took a number of days between each calculation, which was 1, 7, or etc. And I divided the difference by the time. And also for normalizing the results of decay for different stores, which obviously have different amounts, different sums of values, because the amount of a single transaction is quite different for multiple stores, varying from 1,000 to 1 million and over. So here we take a natural logarithm of the difference amount and also calculate the same average and the time-dependent average. Then, moving on from here, we calculated the window statistics, or how they're called, sliding or moving averages, which is basically we move to crawl all the transaction data for those 3 months period for a single store, and we aggregated, basically based on the moving average, the mean for all of those transactions within each sliding window. And further, based on this sliding window statistics or a feature, how you want to call it, we add some additional features. But first of all, we add for each of the periods as seen, like an aggregated statistics format, a sum, a median, and a mean, or an average. These things do not potentially introduce any leaks and will further be really useful within our calculations. And based on the moving average statistics for this 3 months period, we obviously take for each of the moving averages of different size, we take last days from 1 to 46 and calculate a mean. So those were all of the features that I added at this step. We aggregate all those features into a dictionary for each store at each period. And then we basically just make a data frame from this dictionary. So here you can see an example which looked like how it looked like the moving average of 7 days. We take the last 14 days for this moving average and calculate the mean for this exact moving average. Moving on to the next step. We took all of the features that we got from the previous step and we merged it into our original datasets, turning it into a new variable based on the group ID and the store ID features. Group ID, if you forgot, is one for the basically the quarter identifier, and the store ID is obviously the store. Then we set the date as an index once again, and we sort our data frame based on it. Then we aggregate all of the data from the original dataset once again by a 3 months period, or if how is it here by one quarterly period which started in December. Here are all of the aggregations that were done as this step. So basically, sales current are sales during the current period. Sales mean, median, etc. are also all the statistics for the current period that we calculated during the previous step. That were calculated during this step, obviously. So it's also basically the maximum number of sales, the maximum amount of transaction during the 3 months period, the mean amount of transaction, mean average deviation, standard deviation, etc. Basically, at this step, we're trying to introduce as many statistical features for the transactions as possible to further allow the model to gain more easy splits based on different features. Here also where I aggregated all of the statistics done in the previous steps, like holidays, work days, and later we'll find that weekdays and cards as well. I basically decided to represent the statistic for 3 months as a percentage of all of the days which were holidays or work days, and the raw amount. Also, we find the number of unique customers for each of the 3 months periods, which obviously tells us something about how stores are performing. And the dates, there's basically a range for each of the series and where it starts and where it ends. So here we're doing the same thing for the dummy columns, which are the card columns and the weekday columns, and we aggregate them all as mean, meaning that we know that which percentage of all of the transactions for a 3 months period for one store which was done by which card company or during which weekday. And after that, we also, as this one is easy, that we just aggregate the values that should be kept the same for all of the transactions for within each store as by taking only the first value for all of them. So this includes these transactions and also some of the aggregated statistics for store, like maximum of the transactions, sum of the transaction for all this for the store, and well, basically the ones that were calculated at this step. So moving on, we do all the aggregations here by the same granularity of 1/4, and well, we group it group by quarters and stores. Then we use our aggregations, which we described from the previous step, and we drop the level to avoid having columns which were multi-level indexes, which were with multi-level indexes. But at this point, we only have about 200 or 300 features. We obviously want to, or even less, probably about 100. So we want to introduce some new features which would allow us to show the velocity or the difference between each period, each 3 month period and the previous period. So we add the features for the, well, this is obviously a number of periods. So for example, here we calculate a difference between the current store and the stores that were as in previous period or two previous before, or and so on. So basically here we calculate the difference between the current store and some of the previous periods for that exact store. We do it by calculating just throw difference, by just adding the value that was raw value for the last one period, last two periods, etc. And then also calculating the percentage difference. Then we also add the statistics for the difference from which the last store got from his previous store. This part can actually get quite complicated. And basically the same, we get the statistics how the previous store was different from his own, how the previous period was different from his own previous period. It's basically, those are just this, well, the first and the third line for the previous store. Then, moving on from here, we also calculate how the percentage, how did the percentage of the store of the last period done for the current period. The decay between the periods, it is calculated the exact same way as we calculate the decay above, and also the, well, logarithmic value for the decay. And here as well, we calculate the legs, which are just the raw values for the previous for the previous periods. We calculate them for, well, the set of the columns that is described here to know the statistics that we had for the previous periods. Then after that, we add some additional features that were based on the feature interactions. So this feature included the sales range, which isn't based on the feature interaction, it's just an important feature, which tells us for each of the stores basically the difference between the minimum and maximum amount of transaction. Then there is a mean percentage of which this sales mean percentage tells us how each of the periods, which percentage of it takes from the average for the period takes from the overall average, so how it's different from the store performance overall, and the percentage of unique customers that when doing sale that were buying things during each of the periods between the overall number of sales for the period. So moving on from here, I decided to add rank features which basically just ranked all of the stores between the periods based on how, well, just based on the values for different fields. For the transforms, for example, it just ranked all the stores based on, for example, the sum of the transactions for each store and etc. And here we did one of the feature interactions as well. This one is range is not an aggregative or a periodic feature for the store, it's just a global feature for each of the stores. And here we calculate how the sum of the last. It's just an interaction-based feature, so there isn't too much logic based on it. It just was introduced after research of the feature interactions. So it just the amount for the last days of the period, the sum of the transactions during the amount, how well it performs, dividing by which percentage does it came from the overall sales for the period. Also, we added rank feature based on range. So range is just the difference between the maximum minimum value of the transactions for each store, and we just ranked all the stores based on the difference. And after that, this one is purely a feature interaction feature as well. We just divide sales during each period by the overall ranking value for each of the stores based on the aggregated amount of all of the transactions. Then here we drop the fields that introduce potential leaks, which are obviously the sum fields that contains all of the aggregated transactions, and the size fields and contains the overall number of transactions, which, well, basically if you know the averages, allows us to calculate the sum. And reset the index and continue to the splitting the data for the training and testing validation datasets. And basically in this part we have finished all of our preprocessing, but this is the part that I came back a lot of times to because of well, basically because it's the part that requires the most tuning. This one is the settings for the model. So basically, splitting into training, testing, validation dataset is not too interesting. We just split each of the we just split the data based of the periods into multiple models. There are two ways to split the data. Obviously, for a time series, you can't just split it randomly. You have to split it either by using an expanding window from the very start of the time series, or using the sliding window. So the difference is obviously if you use an expanding window, you have one period of 3 months for the train, 1 period of 3 months for the test, and 1 period of 3 months for the validation of the test. If you have a expanding window, if you're using it, then you are just expanding the training dataset by 1 month each of the times. If you're using a sliding window, that you are just moving the training dataset by 1 period each of the time, and it always consists of 3 months, or probably more, because I also introduced the training multiplier. But my resulting model used the one training multiplier, which obviously means that it uses 3 months period and the expanding window. So after we gain the splits, we are going to do the first modeling. As I used the trainer GPN model, I tuned all of the parameters manually. There are also things that allow you to tune the parameters automatically, like hyperopt. But obviously, you should understand the value between the parameters, because just tuning all of the parameters would require an enormous amount of time. Here's L1, which is basically a metric for my mean average error. Here I wanted to encode some of the categorical features, but the LightGBM actually performed worse with the categorical features introduced, so I decided just to leave it. Oh wait, no, I actually used this model, but later I decided to drop them actually. So, moving on to the next step. Well, all of the values for all of the parameters, which were basically tested after many tests that were set to be this way. The learning rate obviously prevents the model from overfitting, as well as the number of leaves and the maximum depth, the metric which is our Maya. And also there is a difference because for LightGBM it can optimize just regression, but here it optimizes the L2 metric, or it can optimize the Maya-based regression, which is for L1. So we just have only 100 iterations between the early stopping. If our parameters are not increasing, the overall number of iterations is 6,000, which is pretty large. It probably should be dropped down, but this model proved to show best results based on these parameters. So in here we just train the model for the number of train test splits. So where to go here should be, we just retrain the model 8 times to gain an estimation for each of the model how it performs. So here we are able to see is that the model is actually performing quite well regardless of whether we're within the expanding window. It first of all drops the mean absolute error drops pretty significantly, but we are increasing the time value for our series when our window is expanding between each model. But at the end, it actually came back to being pretty well, just as it was in the original. And the reason for that is that because between each of the series we have different stores. So during when we're using sliding window at one model, it uses only 1 month of data, and there are omitted some of the transactions data that actually adds noise to the data or have some huge range of values that are really hard to predict and split between the iterations. So that's why if we just had the same number of stores all the time, between all of the iterations, between all of the models, or over the whole time series, it would obviously perform better when we increase the amount of data. And here we show the aggregated statistics for all of the models. So basically, it's not a very great thing here that the validation model performs much better than the training one, but it may actually also be a result of just an expanding dataset and including the different kind of stores. So, moving on. Here we evaluate our model. This one was also obviously a step for the evaluation. The most important for us from here are the mean and the standard deviation, as well as the minimum and the maximum for model performance. But here we see that basically our model performance is pretty close between the iteration for the train and for the test, but it performs pretty poorly between the train and validation themselves. So the validation performs much worse than the train one. Here we are able to view the features that introduce the most gain into our model. This one is the feature that we did through the feature interactions, the current sales divided by the rank. And then it's obviously the rank of the sum and the current sales. So basically these three features we're getting all the gains from these three features. But if you go further, they have even more impact. But sometimes some of the other features, like the sales for the last days period of each period, etc., gain more importance. So for the last model, which I use for the prediction, the the sales for the last 28 months from the previous months and for the last actually 14 months from the previous period proved to be most useful about amount with the sales current and trunk sum. Here we evaluate the performance of the model, how it compared to the training test validation dataset. And it actually did pretty well, because even if the the values themselves for the training and validation dataset are quite different, if we divide the training metric by the validation metric, it's actually quite close to zero. And obviously, the better the performance of the model, the closer the line should be. This metric is actually great for estimating, giving you an estimation of which should be your number for the number, or which should be the values for a number of iterations and for the early stopping value. Because here we're obviously seeing the overfitting for the training model in comparison to the validation model. And here I plotted some of the predictions for each of the store, or not just the predictions, but the prediction error. And here we're able to see that most of the store are predicted pretty well within the error of 200 Maya, which is pretty great. But some of the stores are going a lot over this margin and are basically influencing the overall outcome for our statistics. So that gives us a thought that, first of all, we can either separate the store from the poor performance from the rest of the stores and train them separately and see if it gives us a better performance, or we can leave them with all of the stores and mark them as some kind of an outlier to allow the model to train based on them more efficiently. And that's the approach that I have used later. And here I just took the stores that were performing worse among all of the data sets. So here, yeah, it's basically the statistic for each of the stores, the ones that were performing better. Average, they were performing poorly previously, but they were performing quite well on this dataset. But the error for them was with negative value. Then there are stores that were performing average across all of the trains and validation model, and there are stores that are for which the actual Y value or the target value is much higher than the predicted value. Here is one of the most important parts for feature-based research. It's obviously the feature interaction. So here I use the SHARP framework for calculating the feature interactions based on the SHARP interaction value. And here it allowed us to basically see how well are the feature interaction between each other. And so we see that basically there are not a lot of feature interactions, but I think the feature interaction-based features for those values like rank sum and sales current, for example, allowed me to gain an improvement of about 50,000 Maya for my model. And here is a step where we are adding error-based features. So for the error-based features, I just take all of the models and their performance during the training, during the test, and add two features basically for each of the stores, how well it performed, which was its error for the training dataset, and which was its error for the validation dataset. And then I merge those two, getting the fields error X, error Y based on the store ID. After that, I add some additional statistics, basically how well the store performed during the validation and how well divided by how well it performed during the test, the training, the sum of all of the errors, sum of the errors between training and test, and the average of the errors between training and test. Well, there's basically features that allow for the model to easily split, the more easily split the stores that were performing poorly from the rest of them. Later, I introduced the quantile split. So here, we're above here, we're able to see that actually it's only a lower percentage of our stores that is performing really poorly, and here as well. So at the top and the bottom part. Then we have some stores that are performing averagely, some stores that are performing pretty well but leaning towards the negative, some stores that are performing really well but leaning towards the positive error, and well, basically the same, performing average but leaning towards the positive, and performing very bad, leaning towards the positive. So that's exactly how I divided those values into the quantiles, by 5% quantile, 20% quantile, which ended in leaning towards negative. Here we just have well performing towards the negative, well performing towards the positives, with the center sum, well, basically 0 for both of them is somewhere in the center. And here are some of the worst performing stores, obviously. 5% of the worst performing stores at the beginning, and 5% of the worst performing stores at the end. And here we do a quantile cut, and well, that's how we introduced our error-based features. For each of the features that we introduced above, we are basically doing the same quantile cut. And all that's left to do is that we retrain our model based on our error-based features, and we should gain an improvement. For the training dataset, we gain an improvement. If we look up here, it's about 500s, and for the validation dataset, it's about 300s, if I'm not mistaken, which is quite great, considering that we're using a logarithmic value of the mean average error. And all that's left to do is basically to do with the submission. How it's done is, well, for all of the stores that don't have sales over the last 3 months, we just impute 0 value. For all of the stores that have sales over the last 3 months, we average our prediction with the sales over the previous 3 months, which is, first of all, is post-processing process, which, well, is obviously not a very good thing, but, well, if it works, it works. And after that, we just and it also helps us to deal with the outliers for the stores where we really missed the prediction mark really hard. And well, basically after that, we just write those values to CSV, and that's the end of this code introduction. And I'm sorry that it took quite long to get through all of it, but I hope it proved useful to some of you. You would also be able to find the later versions of my code on my GitHub. I'll try to leave it somewhere here and introduce some of the additional features that may have improved the model performance. Such features may obviously include things like truncating SVD, the values that didn't show any of the impacts which we see during the game. For example, all of the features that we don't really gain quite a lot of gain of, we can just combine them with the same matrix and lower the dimensions of those matrices by truncating the values to gain, well, probably some more important features. Also, it was possible to calculate some of the more easy and naive models, like lasso regression model, for example, for each of the stores, and use its prediction as a feature for the gradient boosting model. It was probably possible to gain better results with after RIMA as well, but the RIMA proved really quite hard to tune towards this model, so I'm hoping that one of the people on the leaderboards is having a Pyramid RIMA or some other kind of ARIMA solution that I would be able to learn from. So thank you very much for staying with me for those 40 minutes, and I'm hoping to see you in the future competitions. Thank you.